Hello everybody, my name is Ruspe Aminian, Research and Development Engineer at Sensilo. Today we will discuss the topic of PFAS in water. In this video we will explore what PFAS are and why they are so important for the water industry. In this video you will learn where PFAS come from, what their impacts are on human health, and how they are regulated. Additionally, we will discuss rapid detection method and water treatment options. PFAS stands for per and polyfluoroalkyl substances. There are around 4,700 different chemicals in the PFAS family. And they all have two things in common. One, they are all man-made and they contain linked chain of carbon and fluorine. Due to the bond between carbon and fluorine atoms in PFAS chemicals, they don't degrade easily. They accumulate in the human body and environment and very stable in water. That's why some people call them forever chemicals. PFAS chemicals were invented in the 1930s and found to have some useful qualities for consumer products because they repel oil, water, and grease. Companies use these chemicals in many common items, such as stain-proof rocks, pizza boxes, for food packaging, think microwave, popcorn packages, and some types of dental floss and non-stick cookware. The two PFAS chemicals you're most likely to hear about are PFOS and PFOA. Human health. PFAS are present in drinking water, groundwater, freshwater, soil, and vegetation. Because these chemicals have been used in many consumer products for many decades, most people have been exposed to them. The chemicals most likely enter our body through the food we eat, for example, microwave popcorn, food in takeout containers, or fish from contaminated water. But some people are exposed by a highly contaminated drinking water. According to Laurel Shader, a scientist at the Silent Spring Institute in the USA, people can also inhale PFAS-contaminated air or dust. According to the US Center for Disease Control and Prevention, the CDC, only a small amount of PFAS can be absorbed through your skin. Studies estimate that 98% of Americans have detectable levels of PFAS in their blood. Scientific studies such as those by Laurel Shader have proved strong evidence that PFAS exposure is linked to elevated cholesterol, damage to the liver and kidneys, effects on fertility and low birth weight. Research also suggests that exposure of PFAS chemicals might suppress the immune system of young children, potentially make vaccine less effective. Regulation. The detection of PFAS in humans has raised international concern and has led to the creation of global restrictions on the use and management of PFAS. But specifically with regard to drinking water, the EU has recently adopted the revision of the Drinking Water Directive 2020-2184, which includes a limit value of 0.1 microgram per liter for a sum of 20 individual PFAS, such as PFOS, PFOA, PFNA, PFBS, and etc., as well as a limit value of 0.5 microgram per liter for the total PFAS concentration. Detection and monitoring. Multiple laboratory-based methods exist for sensitive and selective detection of PFAS in a variety of matrices. But these methods are generally very expensive and require a laboratory and highly trained personnel. there is an urgent need for fast, inexpensive, robust and portable methods to detect PFAS in the field. For example, one of the most common methods for PFAS detection is high-performance liquid chromatography, HPLC, in conjunction with electrospray ionization mass spectrometry, MS. But the costs of this type of analysis are really high. Therefore, more economical and reliable methods have drawn attention. PFAS sensors. Sensors to detect various PFAS species have been developed, as you can see in the table. Actually, further developments are ongoing and will lead to more and more sensors that are able to detect a variety of PFAS compounds at very low levels. One of the speakers at our PFAS webinar is Dr. Najma Karimian at the University of Venice, Italy. She will explain in more detail the principles behind the molecularly imprinted polymer-coated gold electrode, MIP, as shown here at the top of the list. Treatment. A wide range of treatment technologies are expected to effectively remove PFAS from water. The most well-known technologies are presented here. Activated carbon is commonly used to absorb natural organic compounds, taste and other compounds and synthetic organic chemicals in drinking water treatment systems. Activated carbon is an effective adsorbent because it is a highly porous material and provides a large surface area which can absorb contaminants well. Also, the costs of activated carbon treatment are relatively low. Activated carbon treatment has been shown to effectively remove PFAS from drinking water when it is used in a flow-through filter mode, after particulates have already been removed. US EPA researcher Thomas Seps says granular activated carbon can be 100% effective for a period of time. Depending on the type of carbon used, the depth of the bed of carbon, flow rate of the water, specific PFAS you need to remove, temperature, the degree and the type of organic matter, as well as other contaminants in the water. Another treatment option is anion exchange treatment using resins. Ion exchange resins are made up of highly porous polymeric material that is acid-base and water insoluble. There are two broad categories of ion exchange resins, cationic and anionic. Positively charged anion exchange resins are effective in removing negatively charged contaminants, such as Pfas. Ion exchange resins are likely tiny powerful magnets that attract and hold the contaminating materials from passing through the water systems. Negatively charged ion of Pfas are attracted to the positively charged anion resins. Anion exchange treatment has been shown to have a high removal capacity for many Pfas. However, it is typically more expensive than GHC. High-pressure membranes, such as nanofiltration or reverse osmosis, are extremely effective at removing PFAS from water. Reverse osmosis membranes have a smaller mesh size than nanofiltration membranes. The main difference between these technologies is the membrane permeability. A nanofiltration membrane will allow certain minerals to pass the membrane, whereas a reverse osmosis membrane will reject all salts to a high degree. This allows nanofiltration to remove particles while retaining minerals that reverse osmosis would likely remove. Research shows that these type of membranes are typically more than 90% effective at removing a wide range of PFAS from water, including shorter chain PFAS. However, the costs of these membrane technologies are relatively high compared to GAC. Aside from these treatment methods, other innovative technologies are being developed, which can effectively removing PFAS from water. In our PFAS webinar, one of our speakers, Tali Harif, will explain on a novel platform technology which has been developed by Purefinity in UK. If you have any questions or comments to what has just been discussed, please send this to support@sciencesensible.app. The recording of this video presentation will be made available in the Sensilos toolbox via www.sensilo.app. And if you're interested in learning more about PFAS sensors or the latest development in PFAS removal technologies, please sign up for our upcoming webinar on PFAS. Thank you so much for your watching.